Hey class, this is Mr. Schmidt with our February 9th session of AP Physics as we talk conservation of momentum and energy. So in order to set up for today's class, I did a number of searches on YouTube trying to look for different examples of this. One of the first ones I saw was actually from an earlier homework question of if you have someone sitting on a big pillow, I don't know what they call this thing, and someone else jumps off of it. We get a nice conservation of momentum or conservation of energy as all this potential energy becomes kinetic. Pressure in the ball is or pillow, because it's an air or a gas, it applies pressure in all directions evenly, and that energy ends up pretty much this kid who's sitting in the big pillow over here. So we can see a real fast little video here. If you watch it yourself, you'll get to hear all the family members laughing at what's going on here. Okay, conservation of energy, good example of that one. So that's what we were working on last semester, and that's going to come into play today. But what we're really thinking about is conservation of energy and momentum put together. So one of the keys is to keep track of what is the difference between impulse and momentum versus work and energy. So we had these two charts that we talked our way through in class. So the answers being that impulse is the product of force and time. Work is the product of force and displacement. Impulse changes impulse is the change in an object's momentum, and work is the change in the object's energy. And impulse is a vector and work is a scalar. So this is going to become important because in momentum and impulse, we have to know, are these positive numbers? Are they all going north? Are some going south? Are some going east? Are some going west? Vectors become very important in impulse. Work and energy and kinetic energy, it is not important because just like we saw on the pillow, if we have potential energy moving to kinetic, it can get displaced and come out someplace else, okay? So work is a change in energy, not just kinetic energy, but it can also be things like potential or spring or stuff like that. So that's what we're gonna try to piece together here, okay? So today we're focusing on momentum, the real MV equals P, and we're gonna see how momentum is conserved along with energy in a collision. Okay, so the reason I keep saying momentum and energy is because this is the question where they say the collision is completely elastic. Okay, it's in the middle of the sentence, in the middle of a paragraph, but it's a very important statement. So this leads off our homework in a billiards game, and we're gonna see this is a very unusual billiards game because the ball is not the same size as the cue ball. In the billiards game, one player hits the cue ball towards another, and the cue ball has a mass of 0.3 kilograms. And it hits the other ball with a velocity with 2 meters per second. If the collision is completely elastic and the cue ball travels with a velocity of 0.07 after the collision, what is the mass and velocity of the other ball? Okay, so if we look at that question, we can think about how is this drawn, how is it set up? So we have this object, this cue ball, with a known mass and a known velocity, and same mass, another different known velocity going throughout this system. So we can find its impulse, its change in momentum. This object, though, however, we don't know the mass and we don't know its final velocity. Okay, we do know it's a collision, so it automatically means momentum will be conserved. So we can set it up with our momentum of each initial condition and momentum of each final condition. Okay, and then we can start plugging in numbers and see what we come up with. So it starts at rest, which is nice. We plug in all of our numbers. We have these two variables kind of hanging over our head that we have to start thinking about. So we start calculating out and seeing what we can find, and what we get is these two variables that we don't have a process. We can't use one equation to solve for two variables. Algebra tells us that's not possible. So we have to kind of start over here and see if we can do something with kinetic energy. So our setup is very similar to the momentum, only now we have kinetic energy. And we can only do this because they use the phrase completely elastic. Completely elastic means this is going to be true. So now we can plug in our numbers again, and we still have the same two variables hanging over our head we have to try to solve. So we start plugging in numbers and we get kind of stuck at the same place where we have some number equal to two variables. So we have two unknowns and we don't know how to plug in for this. So this is when we can start stitching these together. And algebra has a thing called substitution, where we can solve for M2 and say anytime we see M2, we can put this into the equation. Well, I have an M2 right here, so I could put that straight into here. That's what I get. Okay, now I have V squared divided by V, okay, which is going to V times V divided by V equals V. That's a lot of things overhead. So we no longer have a squared, we no longer have a divide. We now have some numbers, one equation, one unknown. Now we can solve for our velocity. Okay, once we have our velocity, we can plug it in to any of these equations and solve for mass. Okay, so what I was hoping to see in class is that you could set up the initial conditions here, and you could set up the initial conditions here, and maybe you got stuck on the algebra after that, okay? But at this point, you need to be able to do substitution and take one equation and plug it into another equation and solve out for velocity, okay? And that's what we're going to see on the homework as well, is it's not always solving for velocity. You could do the same thing and solve for mass. You could not know two velocities, but know two masses. It doesn't matter. If you have any two of these quantities unknown, and the same two quantities unknown here, we have two equations. We're going to solve down as far as we can go, and then we're going to substitute. And that's the system we're going to try to work for here. Okay, so let's switch pages here. Okay, and like I said, I did a lot of searching on the internet for different possibilities. Someone asked, is it possible on the assignment that an object hits, they elastically bounce off, but they hit and they both keep traveling in the same direction? And it's going to have a lot to do with the impact, the masses, and all those kind of things. As you noticed, the cue ball relative to the other ball, that's would be a very weird pool game to play with such different masses. Okay, so someone made an excellent suggestion if I could search up yoga ball or exercise ball collisions, and that is a gold mine of conservation of momentum and energy and amusement. So here we'll see a little 4-second clip of two people with exercise balls colliding. Okay, so we see them both go off in the same direction based on what's going on. Looks like the two exercise balls often go off in an X and Y, or in the perpendicular direction, which would be a great momentum question for us to solve, but we don't have to. We can just kind of appreciate this whole collision as they go running towards each other. Okay. I don't know what that would do to whiplash, by the way. So not necessarily suggesting you do that, but it was funny to watch. The other little video I was looking for, actually the reason I started off on this little Google search is we have a homework question coming up. We've always assumed if we have an incline that that incline is clamped and only the block is moving. But what happens if the incline and the block have no friction and the incline and the surface have no friction? Then everything can move. And again, water makes for a great example of this, of someone who's trying to sit. Okay, he's got an incline behind him. His plan is to sit straight down on this relatively low friction surface with an incline that has very little friction with the water. And we got to see what happens here. Okay, so what do we see? We see all sorts of different movements here as everything without friction behaves differently. Okay, so we're going to have a lot of conservation of momentum for all of these. Depending on the type of interaction, we might have some conservation of energy. And those are the types of things you want to decide as you work your way through these 3 questions. Okay, so hopefully question 2 looks a lot like the one we did in class, except it stars Captain Marvel, personal favorite of mine, and it also has a question that very much echoes the type of wording that you'll see on an AP test. Justify your answer in a clear, coherent, paragraph length explanation. Notice they don't ask for the numbers. They don't ask for what's happening. They just want to know which one's greater and why, and how do you know that? Okay, so that's one of the types of questions you'll see on the AP exam. So that's one of the questions I want us to start practicing now. Okay, and then you'll also see a second question about calculating speed, even though no numbers are given. Okay, so it's a very short homework assignment number-wise, but it will take you a little bit of time, and we will be talking about the answers during storm time. So until then, have a good day, and I will see you later.